So I think the clock is now 3:02. We're given a couple of minutes extra to have people accommodating this time slot. Thank you all for joining. This is our third session on the Eurotech University Alliance Chemistry Series. The Eurotech University Alliance consists of 6 technical universities around and in Europe: Technion in Israel, DTU in Denmark, EPFL from Lausanne, TU Munich from Bavaria, TU Eindhoven in the Netherlands, and École Polytechnique in Paris, or soon to be Institut Paris Polytechnique. Today, I will give the floor to Kumar from EPFL. Please take the floor.
Thank you, Simon. Can you hear me? Hello?
Yes.
Yes.
Okay, great.
Okay.
Thank you for this invitation. I'm just going to quickly introduce myself. I'm Kumar Varoon Agrawal, a tenure track assistant professor at EPFL. Started at EPFL in 2016, so been there for 5 years. Where I'm based is actually 1 hour from Lausanne. It's a satellite campus in Sion, which we call as Energypolis, where we have a small center for folk doing work on energy conversion, storage, and energy efficiency. My group is essentially working on 2-dimensional materials, but overall, if you read the title here, it's the focus has been material chemistry and engineering at the angstrom length scale for high performance inorganic and hybrid membranes, and focus again is energy efficient molecular separation. My group has 3 different subgroups. They're closely working with each other. The first subgroup focuses on graphene, and in particular incorporating precise defects in graphene so that we can carry out gas separation, which requires a sub-angstrom precision, for example, CO2 from nitrogen. The second subgroup works on more ordered crystalline nanosheets. The unique part in this is that they are still atom thick or unit cell thick, but they have well-defined porosity, which can host a particular gas molecule and reject other gas molecules. And there we are trying to develop methods so that we could play with the way the gases transport through the stacked nanosheet films, removing intersheet gaps or managing intersheet gaps in there. The third subgroup works with hybrid materials. There, our promising material is metal organic frameworks. We have recently done some work with metal soaps and so on. And then our focus is to reduce the lattice of framework flexibilities of MOF, but also to reduce the complexity of the synthesis. And I will show you towards the end, if I get time, to get down to 2 minutes for making a MOF membrane. So why we do what we do? Typically, as most of you would know, chemical industry is quite heat and energy intense. And out of the entire energy that is consumed in chemical industry, about half is consumed on separations, right? So our focus there is on the gas separation, and we look at some heat intensive processes, complex processes, and we try to find a replacement for that, or partially substitution for that. I show you 3 examples here, and the talk will focus on these 3 examples. The first is post-combustion carbon capture, where you are collecting or separating CO2 from nitrogen. And this is commercially done by amine absorption. So you absorb amine and then you regenerate the amines, and therefore you get CO2. But this regeneration step is the expensive step. There is a hydrogen production from the fossil fuel, where you are essentially using solvents similar in scheme compared to this. But here you again have to heat or reduce the pressure to release CO2. And then finally, air separation, which happens at large scale quite successfully commercially using cryogenic distillation, but this is already quite complex and more decentralized operation. For example, small scale operation is often desired, which is difficult to do with cryogenic distillation. So our group is focused by this energy scale. So this is generally true. I would not say that this is true in all the cases. But whenever there is a lot of phase change involved, close boiling liquids, membranes are a good solution compared to distillation. Similar for the gases, especially if the gases you are separating, separation has to be done by cryogenic distillation or absorption. Their membranes can bring benefits. One of the things that our group focuses on a lot is decentralized operations. So we are looking at membranes that can break down the processes into more modular approach. The operation is very simple in that case, and the advantage again is that there is no waste that is produced during membrane operation. Okay, so back to fundamentals. So what we are doing in membrane is essentially what you have is a thin selective layer, which is selective for a set of gas molecules, but is a barrier for another set of gas molecules. So what you do is you establish a concentration gradient across the membrane, and based on this concentration gradient and the affinity of the gas molecule, you have the flow. So the whole process can be modeled by a simple fixed law, which is basically the diffusion coefficient times concentration gradient. You can write concentration gradient as Henry's coefficient into delta P over L. This is for the gases at low pressure, so you could use sort of Henry coefficient kind of simplification. So our group is focusing on three of these variables that goes in this equation for flux. The first one is the diffusion coefficient, and if you look at the diffusion coefficient for gases going through this thin film, in most of the cases it turns out that you're dealing with the activated transport of the gas molecule, be it a nanoporous material where this activated transport is the affinity of the gas molecule hopping from one site to another site, or be in the dense material where the chain packing determines this activation barrier. For the other term, the Henry coefficient, we are looking at competitive sorption, and there, for example, CO2 and nitrogen, we are looking at functionalization and so on to improve the gas transport. And finally, the length, right? So this is why the title of the talk is two-dimensional materials, because if you reduce the thickness of the selective layer to strictly to the limit of 2 dimension, there you have the best case for the highest flux. Okay, so our first example is nanoporous single layer graphene, and we like to work with this material, of course, because if you look at a nanopore of graphene, which you can make by removing few carbon atoms from the graphene lattice, it's essentially atom thick. What it means is the gas can transport directly from the gas phase to the from feed side to the permeate side, right? What really happens in practice is actually you have two contributors to the gas at the pore mouth. So you have a gas phase where the gas actually bombards the lattice and arrives at the pore mouth, but also adsorb phase where the gases bombards and adsorb to the neighboring site and then hop to the pore mouth. Once they arrive there, the key factor that determines the selectivity, if we are in the size sieving regime, that is the regime where we are doing the selectivity based on the steric hindrance, is based on the barrier that the gases experience when they are at the pore mouth. And this barrier is dependent on the relative size of the molecule and the pores. This is why I say there is this really excites us, because there is a wide possibility for handling many different separations based on the size sieving, if we can tune the size of these pores to the desired pore size distribution that is suited for a given gas separation. From membrane's perspective, graphene is very attractive because the carbon lattice is quite robust, and it could be used at high temperature, could be used in many conditions where, for example, polymeric membranes, which are the conventional membranes, they are not so ideal. Of course, there are many challenges for doing this. Typically, when you try to create a pore in graphene, you do end up with a set of pore size distribution. So for example, what I show you is a simulated condition where you have a simulated pore size distribution, and what you're reading in this histogram is the number of missing carbon atoms, which are representing the pores, right? So let's take the case of CO2 nitrogen separation. So if you simulate the passes of these molecules through these pores, for example, when I say P6, P6 means a pore that is made by removing 6 carbon atoms, so somewhere from here. P10 and 13 by removing 10 and 13 carbon atom. So what you would see is that this one is too small. So all the pores here are too small for gas permeation, so they are not contributing to the flux. 10 and 13, they're just right for CO2 nitrogen separation. So most of the separation happens from this area. And then once you go to a bigger pore, for example, in the tail side of this pore size distribution, this again becomes non-selective because both CO2 and nitrogen can pass through the pore without any energy barrier, right? So the biggest challenge here becomes that you have to incorporate a moderate to high density of these pores, 10 to the power 10 to 10 to the power 12. And for comparison, I'll give you the density of carbon atom in graphene lattice, which is 3.8 10 to the power 15 per centimeter square. So quite high in comparison to the density of carbon atom, but with a narrow pore size distribution. And of course, then there are engineering issues that you don't want any cracks and tears, right? So just to give another sort of a flavor of the challenge, for example, if you're working here with a zero energy barrier, the relative transport rate with, for example, if you're working here at 0.2 electron volt energy barrier is 2000 times higher. So one pore here would contribute to a 2000 times higher flux compared to a one pore in this area, right? And even if, so if you're on this side, then the energy barrier is too high and you could see that it's really not contributing to the overall transport, okay? So what are the conventional methods that have been used so far for making pores in graphene? So just to quickly review that. When I started my group here at EPFL in 2016, physical etching methods were quite popular to make pores. And these were being adopted to form graphene-based transport devices, membranes. The challenge here is when you bombard graphene lattice with an energy beam, you have to basically break 3 carbon bonds to make a vacancy defect. To break 3 carbon bond, you have to give 20 to 22 electron volt as an energy. And once you do that, you arrive at the edge. Edge has only 2 carbon bonds, and there you require only 13 to 14 electron volt. So what happens is the growth rate of edge, because you have to break only 2 carbon atom, is much higher than the pore nucleation of these pores. And as a result, this becomes very challenging to control pore size distribution, especially if you want to go to a high pore density. So few examples that are worth noticing here. I want to discuss those. For example, the work by Russo and Golovchenko, which was published in PNAS 2012, they were able to make 2 nanometer size pores by doing a decoupled method. That was the state of the art back in 2012. And more recently, I think 5 years back, Park and co-workers, they reported a focused ion beam based method to drill these 3 nanometer pores in graphene, right? So you could see that these pores are already quite big compared to when we talk about the size of gas molecules. So the size of the gas molecules, for example, CO2 is 3.3 angstrom, so it's about 10 times smaller. So of course there is no energy barrier for the gases to go through. As a result, the transmission rate you see is plotted against the molecular weight, and it's in fact fits very well to the bombardment rate of the gas molecule onto the lattice. So it's inversely proportional to the square root of the molecular weight. There has been some work where they have seen size saving. Of course, this started with the micromechanical exfoliation work, for which Gaim and Novoselov got the Nobel Prize in Physics. And taking this approach, Scott Bunch at Boston University, he was able to deposit a 5 micron sized graphene onto a sort of a chamber, and graphene seals this chamber. Then he found a way to inflate graphene by filling the gas in the chamber, and he simply looked at deflation rate of this chamber as a function of what gas he fills inside this chamber. This was sort of an innovative way of looking at transport rate by deflation of this graphene balloon, right? So the way they were making pores, they were basically putting this entire device into a UV ozone chamber, where UV is first forming ozone and then is forming this atomic oxygen, right? In this proof of principle study, they could already show that you can indeed get very nice selectivity between CO2 and nitrogen. So if you compare this number, this is on a log scale, and this selectivity is more than 1,000, right? So for the membrane perspective, this is very attractive, right? But what are the challenges here, right? One, you are using a micromechanically exfoliated graphite, which is only 5 micron in size, so forget about making a practical membrane. Second, UV ozone treatment is done inside a chamber where you have both the chemical and the light, so if you want to scale it up, it's also very difficult. So in our groups in 2016, we started looking at something that we thought were more scalable. So just a gas-based ozone etching chemistry. So we just kept the part ozone because we could fill the ozone in a large reactor without worrying about the distribution of light. And if you look at what happens, if you look at the interaction of ozone with the graphene, it's very interesting. When ozone arrives at the graphene lattice, it forms the epoxy group, and the oxygen leaves from the lattice, right? And these epoxy group have this reaction has a goes at quite a rapid rate, because the binding energy of ozone onto the lattice is about 0.49 electron volt. This quickly chemisorbs with the binding energy of around 0.59 electron volt. So this happens at a quite rapid rate. What is also interesting is once you form this epoxy group, they're highly mobile on the surface. So you start with one, the second epoxy group hovers around and starts to form these clusters to minimize their net energy, and you end up with a trimer of these epoxy. There has been a little work done in terms of understanding how these epoxy group arranges themselves. So I show one of the work from Stefano Fabri's papers, where they showed that the epoxy trimer then converts into the ether trimer, and then it tends to form these ether chain, all with energy barriers less than 1 electron volt, right? And this then continues to progress with even smaller energy barrier. When there is another epoxy group, there is a spontaneous bond breakage, right? But so far, these have been never validated by the experimental data, okay? So in our group, what we did is we did a very simple test. We exposed graphene with ozone at 40 degrees C for 1 hour, plug the sample in the XPS, and you start to see that there is indeed a peak at 286, which could be either ether or epoxy. We do also see that there is semi-quinone. That is what I'm relating to the bond breakage event here. Okay. Then we go into a low temperature scanning tunneling microscope, and what we start to see is very interesting. We do start to see these linear chains, which have never been seen before, to the best of my knowledge, and they tend to have these two blobs at the end, right? So in collaboration with École Marjorie, we started to look at what these chains could be, and it turns out that these chains are chains of epoxy trimers, which are arranged in this zigzag fashion. They cannot be this chain of ether, because it cannot have a threefold symmetry that we see here in this image here. So essentially this becomes very interesting, because at room temperature itself, we are forming these linear clusters, which can then give us the pores when we heat it, right? So here is the example where what happens when we heat it. So these are what we see typically after, for example, if you take that sample, heat it to 250 degrees C, we start to see several of these clusters. Now, what are these clusters? If you do a line scan across this, you would see that there is a height of 2.5 angstrom, and then there is a vacancy, right? So essentially what is happening is these epoxy group, they gather along each other. There is a coalescence of the groups, and then in the middle, you form a pore, right? And then if you heat this to further to 900 degrees C, you are able to remove most of these oxygen functional group, because the stability of epoxy group is only up till 250 degrees C. Even ether groups, they are stable up to 600 degrees C. And what you're left with somewhat semi-quinone group with typical height of around 0.6 angstrom. Okay, so we started to look at then what happens in terms of nucleation and expansion, right? So remember I explained the physical method, which was the bombardment of energy beams onto the graphene lattice, where the energy barriers were very different for nucleation and expansion. So to measure what happens with ozone, what my students did was essentially exposing ozone to the graphene, but at different temperature, and just plotting the rate of buildup of the epoxy group on the all the oxygen functional group on the surface. So you see molecules per meter square per minute. So we normalize it with the time of the treatment as well. And once you do sort of this Arrhenius kind of a plot, you say that you can fit pretty well a line which gives you an apparent energy barrier of 0.67 electron volt, right? So this is the energy barrier for grafting of these clusters, and to get the actual energy barrier, you have to add with the physisorption energy, and it turns out to be 1.16 electron volt, right? So this is why this is interesting. This is interesting because ultimately the pore formation that happens by ozone is by release of CO or CO2 in these structures. And it has been shown by few studies that CO and CO2 releases with an energy barrier of 1.1 electron volt. So this is the data from the Lizet and Baraldi's work, where they did simulation as well as they showed this TPD data, which was quite consistent, yielding an energy barrier of 1.1 electron volt. So as you see, the rate constant, so these are the energy barriers, so they relate to the rate constant of pore expansion, which is coming from CO2 release, is very similar to the rate constant of pore nucleation that happens from formation of these clusters. So this makes it very interesting for ozone, because then your nucleation and expansion rates can be manipulated based on these rate constants and based on the ozone pressure. Right, so our next step was to make membranes of practical dimension. So we looked at the method reported by Prof and co-workers, and since then it has become a very popular method to make graphene at a large scale by chemical vapor deposition. In our group, we now make, we have been making 2 centimeter by 5 centimeter coupons by essentially taking a copper foil and exposing it to methane at 1000 degrees C, where you get dehydrogenation of methane, and you get these graphene grains which grow into each other and form these films. Okay, one of the challenge here, comparing to micromechanically exfoliated graphene, is that there will be always grain boundary defects in these films, right? So this is sort of shown in the Raman data with the D peak, right? And once you have these grain boundary defects, they are already quite large to be permeable. So we have to deal with these intrinsic, we call these as intrinsic vacancy defects, which already have some permeance for hydrogen, right? So they are low in density. The density of these are about 10 to the power 10 per centimeter square, but they are still there when we start to form membranes. Okay, so some membrane data. So when we started looking at this, we said, let's see what happens when we expose the graphenes, CVD graphene, which have these intrinsic vacancy defects, with a small pulses of ozone, right? What I'm showing you is a scale which shows the kinetic diameter of these gases, so that you could look at the data in the perspective of this scale. And so what I'm going to show you is separation of hydrogen from methane and propane. So if you look at the kinetic diameter of methane, it's about 2.9 angstrom. Hydrogen is 2.9 angstrom, methane is 3.8 angstrom, and propane is 4.3 angstrom, right? So when you plug in your membrane, which has intrinsic vacancy defect, you already see that it has some hydrogen permeance. The hydrogen permeance is written in GPU. By the way, 1 GPU is 3.35 10 to the minus 10 moles per meter square per second Pascal. So it's a flux divided by the pressure difference. And then you expose it to only 10 seconds of ozone. What we see is about 20 to 40 time rise in hydrogen permeance, right? So what happens is you start with a density of defect, which was about 10 to the power 10 per centimeter square, and you go to a next order of magnitude density of defect. So it sort of supports our hypothesis that you have a lot of nucleation event, but not so many expansion event. And this is also proven by the fact that we still maintain the selectivity. Before we could not detect propane, but now once we look at the propane, the selectivity of hydrogen and propane is around 200, right? So this is basically now competing with some of the more crystalline materials like MOFs and zeolite, from where you expect a selectivity of 200, right? Once you start to do more longer term gasification, we don't see so much more nucleation, indicating that most of the clusters have formed, and now what you're doing is essentially expanding the clusters. As a result, the selectivity, it drops further. So now, so the way you can look at this is, first you're forming these clusters, increasing the clusters to cover the graphene lattice, and the cluster forms the pore. And then once you do this more and more, you have the cluster expansion. So we'll also looked at this in terms of comparing ozone versus oxygen plasma. Oxygen plasma is one of the common tool in this field. So once you start with the intrinsic defects, you treat it with plasma, you would often see that the selectivity decreases, permeance increases, and if you again do a longer time plasma, the same thing happens, right? But if you do it with ozone, you see exactly a different trend. Both the permeance and selectivity increase no matter what temperature or what condition you use. Even after plasma, there is a increase in selectivity and permeance, right? And the reason is so because although oxygen plasma is sometimes thought of as a chemical method, there are energetic radicals and ions in oxygen plasma which can actually knock out the carbon lattice. As a result, then you go into the again the same area of the physical etching, where the pore expansion rate is higher than the pore nucleation rate. So you'll always see this trend with the plasma, whereas the ozone nucleation rate, the rate constant of pore expansion is similar to the rate constant for the nucleation. And depending on the pressure, you can have much higher nucleation rate. Depending on the ozone pressure, you can have much higher nucleation rate. Therefore, you can go into this direction. Okay, so our next target was to separate CO2 from nitrogen. And as you see, this is much tougher separation compared to hydrogen and methane, where we were looking at 1 angstrom. Now we have to do at this point 3-4 angstrom in terms of the resolution of these two molecules, the size difference of these two molecules. So we came up with this approach and said, because this is a tougher separation, maybe we want to limit the pore expansion. We can do this by doing a short expansion time, but then we also sacrifice the CO2 permeance because the nucleation rate is low. So we said, let's do a combination of aggressive etching, which is high nucleation rate, but we reduce the expansion time. And we did this by sort of going into the millisecond reaction regime, but then going at higher temperature and higher concentration of ozone. So for this, our group built this millisecond gasification reactor. Ultimately, what it is you place your sample in this heated zone, and you have 2 ALD valves, which are synchronized, one for introducing ozone and the other for purging out the ozone. And the whole experiment happens in initially at vacuum, so that you can do this in a uniform way. Okay, so here is a typical pulse of ozone for a 200 milliseconds. So first 100 millisecond, you see the ozone pressure is rising. Then we remove it and then finally purge it with argon to remove the ozone. So we are now going from 10 seconds of reaction time to a reaction time of few milliseconds, right? And when at this time already we were started to look at what happens to the structure of graphene in HRTM. I have to say that this visualization of nanopores in HRTM is quite challenging because typically these nanopores are covered by contaminants from the TM sample preparation process. So we did have to heat it to 900 degrees C to be able to see these pores. So as a result, we only see bare edges. We don't see oxygen functional group in these images. What is very interesting is for each number of missing carbon atom, for example, this is the case of 6 missing carbon atom, we would see several different isomers or several different possible structures. And what was also very interesting is that they tend to follow a statistical distribution, and this statistical distribution tend to follow very well with the theoretical prediction that was recently done by Strano and co-workers. So this was already very interesting because these pores tend to exist in they tend to exist in a particular form and prefer one pore, one shape, than the other shape. If we plot this, if you combine all the isomers and then you start to plot the number of missing carbon atom, then what we saw here is that most of the carbon atoms were less than 20. Most of the pores had less than 20 missing carbon atoms. What it means is that we had quite a few pores in this area which were selective for CO2 nitrogen, but we also had quite a few areas which we thought were not selective. But remember, there is no functional group here, but when we do ozone etching, there are functional groups. So this is why we believe that this could be still very interesting for gas separation. And indeed it is. So when we plugged this in the gas permeation module, we immediately saw that there were much higher transport rate for helium, hydrogen, and CO2 compared to the transport rate of nitrogen, methane, and propane. By the way, this is a log axis plotted as a function of the kinetic diameter, right? So hydrogen is faster than helium because hydrogen absorbs slightly a little bit more than helium, which essentially doesn't absorb on the lattice. And then CO2 tends to decrease because CO2 has a larger size than hydrogen, but still absorbs much more strongly than hydrogen. So there is a clear cutoff between CO2 and oxygen and nitrogen. So we did some more experiments in terms of cutoff adjustment. So in our lab, we play with this cutoff in graphene quite a bit nowadays. So this was done in situ. What we did is we loaded our membrane module. So what we have is on the permeate side, we are sweeping whatever crosses the membrane with argon at 200 degrees C. On the feed side, we have CO2 and nitrogen. And this is what you see. So CO2 goes faster, then nitrogen. So CO2 is in blue, nitrogen is in green. And then we said, maybe we can increase the tail of the pore size distribution by removing few more carbon atoms so that we can have a faster permeation rate of CO2, but still not increase nitrogen so much. So this way we can increase the permeance while maintaining the selectivity. And this is exactly what happened. So we chose a gas which is known to be not very reactive with graphene at 200 degrees C. So in this case it is oxygen, and if you look at the etching rate constant of oxygen at 200 degrees C, it's quite sluggish. Essentially in 2 hours you're going to expand the pores by 0.3 angstrom. And this is somewhat exactly what we see, is that when we do this, the cutoff is still falls beyond CO2. But if you now look at what is happening between oxygen and nitrogen, oxygen starts to pop up, and the slope that you see between the cutoff of oxygen and nitrogen, it starts to increase. So oxygen, so the oxygen is now somewhere midway between CO2 and nitrogen. And we believe, so for example, here the selectivity between oxygen and nitrogen is between 3 and 4. So this could be still a method in future to further fine-tune this method to even look at the separation of one of the most difficult membrane-based separation of gas molecules, which is oxygen and nitrogen. The second point I wanted to emphasize is that this is definitely etching and not the functionalization of the pore, because we actually did the functionalization by decorating these pore edges by oxygen molecule, and this is you can do at room temperature with ozone treatment. And when we do that, we see that the flux doesn't increase, but in fact it decreases. And this makes sense, right? Because you start with a pore and then you're shrinking the pore size by decorating the edges, and therefore the flux will tend to decrease. More recently, we are looking at mathematical modeling of the etching that happens, that is the pore nucleation and pore expansion. So the nucleation rate, you could say that it is a function of the ozone pressure and the rate constant. The rate constant is the one that I explained to you before. That is the formation of cluster. And the pore expansion is proportional to the rate constant, which is the removal of CO2 from the lattice, CO and CO2 from the lattice, and the ozone pressure. What we realize, it turns out that the pore expansion rate is not directly proportional to the pressure, but it is the proportionality constant is less than 1. In fact, in our preliminary studies, it turned out that this n is about 0.5. We believe this is the case because when you react a pore edge with ozone, it can essentially impart more than one oxygen group on the pore edge, whereas in the nucleation, one ozone molecule gives you only one epoxy group. Anyway, so this was quite interesting because what you see is a pore expansion is a stronger function of pressure. Pore nucleation is a stronger function of pressure compared to pore expansion. So we said, maybe we can play with the pressure a bit to further fine-tune the etching conditions. And we came up with a very counterintuitive method by saying, let's go to a higher pressure and let's go to a higher time, right? So my student said, or I think I said to my student, is that this will never work, right? Because this should give you much larger pores compared to when you have a one single pulse. But this was not the case. In fact, what we had is we got the best pore size distribution by having a square pulse at higher pressure. And the reason for this is if you look at the nucleation densities, it's directly proportional to the area under the curve. So you're creating a much higher nucleation density, and those nuclei are then essentially consuming all the ozone that is coming onto the surface. So the pore expansion effectively slows down, and therefore you get much lower, much better pore size, much narrower pore size distribution compared to a single pulse. And this is something that you can verify by looking at the CO2 nitrogen selectivity as well. So this is the control case, this is the single pulse, and this is the case where we use a much higher pulse, where you could see the selectivity goes from about 15 to 20 to about 30 to 40. Okay, so I will quickly go through a few more things that we do in terms of transport engineering and adsorption engineering of graphene. So one of the things that we realized that in CO2 and nitrogen separation, we can use the fact that CO2 adsorbs much more strongly onto the surface compared to nitrogen, right? So we were looking at modeling the gas transport of CO2. So what we do is we essentially make several pores, and we look at what happens to the transmission coefficient of CO2 through the pores, right? So as you see, when the pores are small, you are in this energy barrier regime, so the transmission coefficient is quite low. and then it increases exponentially with the pore size, right? At some point, the energy barrier goes to 0, and the net transport rate is then determined by direct gas phase transport and adsorb phase transport where there is no energy barrier. If you compare these two rates, adsorb phase transport and gas phase transport for CO2 and nitrogen, you would see that there is a distinct behavior for nitrogen, that the gas phase transport and adsorb phase transport for nitrogen are very similar. And in the case of CO2, the adsorb phase transport is an order of magnitude faster than the gas phase transport, right? So what is this gas phase transport? This is the direct impingement of CO2 onto the lattice, right? So the gases can directly go through the lattice. So we said, can we then stop this gas phase transport and then benefit further in terms of selectivity between CO2 and nitrogen? So my student came with a simple idea. Why don't we mask the graphene lattice with something that is CO2 permeable, right? So for this, we took a polymer film. This is a polymer with intrinsic microporosity. This already has very attractive CO2 nitrogen selectivity, as you can see here, and a pretty decent CO2 permeance. But we wanted to sort of proof of principle, we wanted to see what happens, right? So in this case, we made membranes with plasma. So here is a graphene nanopore made with 1 second plasma. Here's the, and then what we do, we take the PIM1 and cover it on top of graphene. What we see is something very interesting that happens. Once you cover it with PIM1, you see a sharp rise in the selectivity. This is an increase more than 3-fold, right? So this is quite attractive if you think of the membrane perspective, because selectivity of 10 and 30, typically in the membrane literature, will be a very different material, right? And then this is also very helpful for the polymeric research, because several polymeric membranes which are just below a certain target area can be improved by using this strategy, right? So this synergetic enhancement is essentially then arriving from the fact that we have now killed the direct gas phase transport, because the gases now, they have to adsorb on the polymeric domains and then arrive at the nanopore. Similarly, we could also tune the adsorption selectivity. So we could tune the competitive adsorption of the pore by actually functionalizing the pores with different molecules. So our first proof of principle study in this case, we looked at the known molecule in the literature which are quite conducive for CO2, selective CO2 adsorption. So we looked at polyethyleneamine, which is actually used commercially, for example, for direct air capture of CO2, right? So what my students did here is essentially grafted an extremely thin film. In this case, it was 3 to 10 nanometer thick films of PEI or PEG-BA. So both of them have a high number of nitrogen groups inside these chains. In PEG-BA, you have oxygen group, and these improve your competitive sorption of CO2 compared to nitrogen. And as a result, what we saw was very interesting. Even when the pores were quite large, for example, 1.8 nanometer, this is not expected to give you CO2 nitrogen selectivity, right? But then you will have few pores at the tail pore size distribution, which will be quite small. They will contribute to the selectivity. And then on top of that, you mask this with these functional group, and then you arrive at selectivities which are about 40 and 50, right? So, and what we saw is as we were increasing the porosity in graphene by going to a higher pore size, the permeance goes up and the selectivity goes down, because now you have much lower pores at the start of the pore size distribution, which will sieve CO2 from nitrogen. More recently, we have further improved on this method. So these pores were generated by oxygen plasma, where you get a much broader pore size distribution. More recently, we have been able to make these pores by ozone, where you get a much narrower pore size distribution, and we could further enhance the selectivity and permeance of these membranes. Okay, switching topic a bit. So these were all the methods that we did from where we synthesized the graphene lattice by etching the graphene lattice, right? Remember I said at the start that there are these intrinsic vacancy defects in graphene, and so our group also started thinking, can we further increase the density of the intrinsic vacancy defect so that we just have one step of synthesis? We synthesize graphene where we have these lot of grain boundary defects, and the vacancy defects between the grains would then permeate the gases, right? So for this, we came up with an approach that why don't we use a nickel foil, which has a much higher adsorption capacity or solubility capacity for carbon, And this is known to synthesize multi-layer graphene by segregating the solubilized carbon when you cool it down, right? The trick that we did here is by essentially limiting the amount of carbon precisely on top of the nickel foil. So what we did is we coated about 100 nanometer thick polymeric film onto the nickel foil, heated to 500 degrees C for 1 hour, and then we just waited to see what happens, right? So essentially what happens here is because you have such a small dose of carbon atom, the nickel foil here is 25 micron thick. The carbon atoms, they mostly diffuse through the nickel foil. The residual one, they precipitate onto the surface. And because our dose is so controlled, we only have few small grains of graphene. These grains will essentially then meet into a single layer graphene. And there you have essentially extremely high pore density, right? The pore density here is essentially the inverse of your the grain density. The grain density in this case gave us a pore density of 10 to the power 12 per centimeter square, which was much more higher than 2 orders of magnitude higher than what we were getting by our previous approach, right? And this was very attractive because most of these pores are in the size of 4 to 20 angstrom, right? So we could still make a very attractive membrane. So by masking approach, by coating these pores by PI, so you could say that our permeance is quite attractive, around 8,000 GPU, and we are still getting selectivities which are about 30. Okay, so these were all the material chemistry that I described. Where we are in terms of the engineering. When we started in our group, graphene membranes were about micrometer scale in dimension. Especially you would typically use these micromechanically exfoliated graphene or a single pore, and you will try to study the transport through these 5 micron domains. In 2018, we reported this approach where we said we can circumvent the cracking issue in graphene membranes by essentially leaving a porous support onto the graphene. And this allowed us to make a millimeter scale membranes for the first time. And we could study several transport properties. All the studies that I showed you on ozone, several of them were done on this millimeter scale. In our lab, now we can routinely make centimeter scale graphene membranes by again now adapting this reinforcement process to using a polymeric reinforcement, which is much more permeable, right? I'm very excited to share that we are now going to work on a pilot scale membrane. This is an ongoing project by a local industry in Switzerland, GAZNAT, which is a natural gas distribution company, as well as some support from the Swiss government, Canton of Valais, where my satellite campus is located. So here we are going to, so this project is already ongoing, and our target is to capture about 10 kilogram of CO2 per day. So a little bit more practical perspective, why we think that we are at a very interesting stage in post-combustion capture. So we did a techno-economical analysis recently for capturing 0.5 million tons of CO2 per year, targeting somewhere between 10 to 14% CO2 in the feed. If you look at the current commercial process, this is amine-based CO2 adsorption, and the capture cost falls somewhere between $48 to $111 per ton of CO2. Now this is very complex operation, and you have to deal with amine loss as well as degradation of the amine from the oxygen that comes in the flue gas, right? What we were able to show is because our membranes are highly permeable, we can use the vacuum pump in the permeate site, and we can do this because the permeance is quite high and we can still manage a very small membrane area, right? And what vacuum pump does, it improves your energy efficiency. So we could cut down the cost of separation. And what I'm showing you is the carbon capture penalty as a function of the CO2 concentration in the feed from 10% to 14%. And so this is despite the fact that we assume a quite conservative membrane cost, which is $500 per meter square, compared to polymeric membranes, which are about 10 times cheaper than this. So where we are in terms of CO2 nitrogen separation in the lab, so what I show you is a sort of a plot which is known in gas separation community as a Robinson plot, but equivalent of that in terms of CO2 permeance, which is in gas permeation unit, right? So This is a Robson upper bound for polymeric membranes calculated by converting the permeability of polymer into permeance by multiplying by its thickness. And then what we show is that this entire area is being populated by the nanoporous graphene membranes that we have developed in past 3 to 4 years. Whereas the other state of the art, for example, here, this is the membrane reported by Tianjin University, where they make these metal complexes inside the polymer. This is the commercial Polaris polymeric membranes, where you get a permeance of 2000 GPU, and the techno-economic analysis that I just showed was based on a permeance of 10,000 GPU and selectivity of 30, which we think that we are quite close in terms of achieving. Okay, so I will take a very quick explanation of what we are doing in terms of nanoporous nanosheets in our research group. Essentially, the focus is to develop membrane by stacking these nanosheets, but compared to, for example, graphene oxide nanosheet or MXene, the idea is that these nanosheets should be porous, and the porosity should be ordered so that we can get selectivity based on the size sieving from the pore itself, right? So if you look at the stacks of these sheets, there are two directions for transport. One is through the pore, and then once you stack them, there is a gap between the nanosheets. So you always have these intersheet transport. And our group is trying to answer this question: how can we manipulate this intersheet transport channels so that we manage to get selectivity mainly through these pores? So I will maybe I should skip this, but I'll quickly show you a case study where we did this for a zeolite nanosheets. Zeolite, as many of you know, is aluminosilicates. They are typically three-dimensional crystals, and more recently, in I think last 2 decades, two-dimensional zeolites have been starting to pop up, and I highlight some of the frameworks in zeolite where two-dimensional layers can be synthesized or have been synthesized. This was something that I also did in my PhD work, where we synthesized MFI zeolites in the group of Michael Sapatsis. So now we were looking at post-combustion capture. So we thought of investigating a zeolite which could separate CO2 from hydrogen. And one of the candidate zeolite for that is sodalite. And of course, we are not the first one to look at this. Jensen's group has looked at this way back, almost 20 years back, looking at simulation of hydrogen transport from sodalite. And then they arrive at the conclusion that hydrogen can transport through a not too high energy barrier through the sodalite framework with 33 kilojoules per mole, right? My collaborator, Michel Cheriotti, he also simulated a precursor of this sodalite. It's RUB15, essentially layers that condense to form sodalite, right? And what we saw was that hydrogen can pass through with an energy barrier of 0.34 electron volts, so very similar to what was predicted through a bulk sodalite. But of course, CO2 will require much higher energy barrier, right? So motivated by this, we synthesize these nanosheets. Essentially, you'd go through a hydrothermal process to make these layers. So these are quite standard way of making layered zeolites. And then we have this method of exfoliating these layers, going through swelling of these layers to reduce the interlayer spacing, and then going through a shearing, polymer shearing process where we can form these uniquely very uniform layers, which are just unit cell thick, right? So this you can see it in the AFM image. The thickness of these layers are 8 angstrom, which is exactly what you would predict when you start to measure from the 2-terminal silanol groups of this nanosheet, of the zeolite framework, right? The nice thing is that this exfoliation process is quite mild, and we are able to make nanosheets that are still crystalline and have no sign of structure damage or structure amorphization. Okay, so once we made these nanosheets, the first goal was to stack them, and once we stacked them, we looked at the gas transport. What we realized that we were not getting hydrogen CO2 selectivity, but we were getting hydrogen nitrogen and hydrogen methane selectivity, right? So we started looking at the transport mechanism. So for that, we measured the activation energy of hydrogen transport. And what we measured was about 20 kilojoules per mole. But remember, I said before it should be around 33 kilojoules per mole, right? So we started thinking what is happening. we looked at the XRD X-ray diffraction from these sheets, and we found that there is a despacing in the stacked film of 11.4 angstrom. And remember that these sheets are about 8 angstrom in thickness, so that means you're leaving 3.4 angstrom in the gap, right? So the CO2 being 3.3 angstrom can easily pass through the pores. And so exactly this was happening. So my student came with this idea that why don't we condense these nanosheets, given that they have a reactive silanol group. So if you heat 2 silanol groups together, they're going to make SiO-Si bond releasing water. And this is exactly what we see in the XRD here. Once you heat this 11.4 angstrom goes to 7.4 angstrom. In fact, the thickness is less than 8 because you're losing the water molecule as a function of once you do this condensation. And then what we see is then we can indeed get hydrogen CO2 selectivity. And this is very nice because by the fact that this is zeolite, we can really go to high temperatures, right? So we can go to 300 degrees C and still carry out this separation. So this is one of the few materials that can carry out hydrogen CO2 separation in a very stable way. This zeolite will not get affected in the same way as, for example, a palladium membrane will get affected when you bring CO and H2S, right? So this was quite interesting for filling in that void for pre-combustion capture. Okay, so I think my time is up. This is my final slide in terms of what we're doing in the metal organic frameworks membrane. So metal organic frameworks, as you know, there's a lot of work, especially from the Yagis group, looking at different metal organic frameworks chemistry and so on. And Caro group and Sapasvis group, they came up with the first MOF membranes in about a decade before, but the MOF membranes were about 20 to 30 micron thick with a synthesis time scale of a day, right? Our contribution to this field is essentially trying to crystallize these films in a much more robust way by cutting down the synthesis time. So we reported this electrophoretic nuclei assembly by forming very thin nuclei onto a porous support so that we can quickly grow these nuclei films, not forming too thick films. Later, we looked at Ostwald ripening of these films by using a flow-based synthesis. Essentially what we are doing is we form these nuclei and then we say we can simply maintain the high precursor concentration by doing this in a stirred tank reactor coming from a continuous flow of the components that form the MOF, right? So in this case, we were able to go from 10 hours to 10 minutes. These MOF membranes perform quite well, but they are still bulk-like, right? The thickness of these MOFs are about 400 nanometers. So very recently, we have been able to develop chemistry where we can now make a unit cell thick MOF, and that too in 2 minutes. So this is not published yet, but hopefully we will be able to tell this story very soon, where we'll show that these MOFs, they combine into each other while making a polycrystalline film while being a unit cell thick, and they show very attractive separation selectivity, something that I cannot completely share at this point of time. Okay, to conclude, hopefully I showed you 3 different examples, 3 different subgroups in my group, one based on nanoporous singular graphene, nanoporous nanosheets, and hybrid materials. And I think the key message I want to give is graphene membranes are quite attractive for doing very difficult gas separation where you require sub-angstrom resolution. And this was possible for us because we used ozone-based chemistry where the rate of the kinetics of pore nucleation was comparable to the kinetics of pore expansion. And as a result, we can now get down to other gas separations. So we are now quite focusing on oxygen-nitrogen separations, but also ion-ion separation and hydrocarbons. With the stacked nanosheets, one of the fields that we are now looking is the water vapor transport, harvesting water from the atmosphere by using extremely high affinity of these nanosheets for water vapor. And finally, with the MOFs, we are looking at also post-combustion carbon capture and hydrogen-nitrogen separation. With this, I'd like to thank my group, my collaborator, Nicola Marjorie, Professor Johan, Michel Chariotti, and Professor Wendy Queen, and my funding agency, especially thankful to GAZNAT, which has funded a lot of our work, and Shell and ERC, which is funding some of the basic fundamental research in my group. Thank you, and I look forward to your questions.